Welcome back. Logistic regression today. We'll start with some challenges of categorical outcome variables, and then we'll move on to topics more specific to logistic regression. With categorical outcomes, it's the case that our data captures only two states of the dependent variable. The reality that lies behind these two states can be pretty much anything. The two states could actually be continuous, like trustworthiness, and we're just coding trustworthy versus not trustworthy. And it could be two things that would not, outside of our study, seem to have much to do with each other at all. For example, whether somebody was sent to a hospital or a jail. When we're dealing with categorical outcomes, one problem we deal with is heteroscedasticity. Errors not distributed normally around each x value, pockets of positive residuals in green where we're predicting too high with our model, and negative residuals in red where we're predicting too low with our model. Moreover, we have inherently poor prediction when attempting to predict categorical outcomes with a line, or at least inherently imperfect prediction, because a line cuts through space where no value exists. Here, most of the predicted y values along this straight line don't exist. Of the two real values, 0 and 1, the model only predicts 0 when x equals 20, and the model only predicts 1 when x equals around 80. So, our want add for a better model here would read wanted a scale bounded between 0 and 1 that has intervening values that make sense. It doesn't make sense to predict 0.6 when only 1s and 0s exist, but it does make sense to predict the probability of the y value, so we want y estimates that behave like probabilities. Let's model not y, but the outcome p of y, or the probability of y. We don't want to predict values less than 0 or higher than 1, so what can we do? How can we get one line that does not violate the basic aspect of calculus that a line cannot produce two y values for just one x while remaining in the bound? Well, our best nonlinear or curved line, given that necessary restriction, would look like this. This is a line that can find, hit, or predict the bulk of observations. Okay, so we need a sigmoid, a line with an S shape. Got it. How do we make those? Well, the typical nonlinear trick here is to use a logit. Note that this is not the only way to do it, but nearly every program you ask will use this method. The logit is the natural log, also called ln, of the odds ratio for y equals 1. Okay, before we take the ln of it, what is the odds ratio for y equals 1? The numerator for the odds ratio for y equals 1 is the total number of observations where y equals 1 divided by the total number of observations. The denominator for the odds ratio of y equals 1 is the total number of observations where y equals 0 divided by the total number of observations. Put more compactly, it's the probability of getting y equals 1 over 1 minus that probability. That odds ratio is transformed into the natural log scale, and this ln transformed odds ratio is the logit. In other words, when your program gives you logit values for predicted y's, they are ln transformed odds ratios, meaning they contain odds information. One just has to back transform them. These are the predicted values we asked for that sensibly behave like probabilities. Nobody asks for logits, their units make no sense. We back transform them to get odds ratios and probabilities. But let's not get ahead of ourselves. An example to illustrate an odds ratio. Let's say for every singular case where y equals 0, we have 4 cases where y equals 1. Our fraction is then 4 observations of y equals 1 over 5 total observations divided by 1 value of y equals 0 over the 5 total observations, which is expressed in probabilities or proportions, 0.8 over 1 minus 0.8, which is 0.8 over 0.2, which is 4. This means the model predicts an outcome of y equals 1 is 4 times more likely than an outcome of y equals 0 for this given input, or modeled value of x. Except most programs will not produce the odds ratio that actually gives us the relative chance of y equals 1. Most programs will give us the logit, which is the ln of that value. So if the model predicts a 4 to 1 chance of getting y equals 1, then the corresponding logit will be 1.3863. This means we would need some grade 9 algebra to actually get the odds ratio from the logit. Specifically, we need to reverse the ln function by raising Euler's constant to the power of the logit. In other words, when your stats program gives you logits, raise e to the power of them to get the relative odds of y equaling 1. E to the power of the logit that the computer program gave you is the odds ratio for getting y equals 1, given the x you put into it. So the program spits out a logit of 1.3863. You raise Euler's constant to that logit, and it gives you 4. So this is an odds ratio of 4. This 4 means that for the given x value, the model estimates that a y value of 1 is 4 times more likely than a y value of 0. But we tend not to think in odds ratios. We tend to think in or be most familiar with percentages and proportions. So we could further transform that odds ratio into a probability, as done here. This would be how one would code it up in R. I have a log regression model object called class 2 model. R is giving me the predicted logit values when I use the predict function, and the exp function, in which the predict function is nested, raises Euler's constant to the predicted logit. Let's place ourselves inside of an example where we can use that formula. My first example comes from something a student asked me in undergraduate statistics. She asked, I did poorly on test 1. Can I expect to do better on test 2? Well, yes, but it depends. One can bring data to bear on the general situation here, but this data would not tell us whether her particular circumstance would place her in an average case or an exceptional one in either a positive or a negative direction. The temptation here might be to look to see whether the test 2 mean is higher than the test 1 mean in prior iterations of the course. If it is, then she can expect a higher test 2 score, but that approach would be a waste of information. She told us she did poorly on test 2, so let's use that information to customize our estimate here. My dataset from the previous time I instructed that course consisted of 151 intro stats students and their scores. To address her question, can she expect to do better on test 2 than test 1, our dependent variable should reflect her simple categorical question, specifically y equals improvement, as coded by the following rule. If the test 2 score is greater than the test 1 score, then that student's y equals 1, or improvement. Else their y equals 0, which is either test 2 score is equal to their test 1 score, or a test 2 score that is lower than their test 1 score. In other words, I computed a categorical outcome variable to indicate improvement, and I called it improve. We will answer her question in terms of the probability of her improving given her test 1 score. That is, we will predict the categorical variable improvement, which is 1, where a student's test 2 score is higher than their test 1 score from test 1 scores. The dependent variable is improvement and the independent variable is test 1 score. We know at first that she did, quote, poorly on test 1, which actually tells us nothing because poor is relative, but let's assume a more objective idea of poorly until we can plug in her specific test 1 score. We can look up her actual score and plug it into our logistic prediction model later. First, we need the model itself, which will answer the second part of our question generally and give us the equation for predicting her own case more specifically later. So we can run the model predicting improvement from test 1 score and get an answer to the question, does a lower score on test 1 predict doing better on test 2? This is us making use of the information that she did poorly on test 1 and seeing whether this predicts improvement. Yes, we could have just looked to see whether the mean on test 2 is higher than the means on test 1, but this is not necessarily helpful. It's a waste of information and certainly does not give us a customized probability, as we will be getting shortly. First, the model. Here is my logistic regression model command. I am creating the model object called class2model by running a general linear model function predicting the improvement outcome variable that I made from the test1 predictor variable using the properties of the binomial distribution. By default, it would be the normal distribution. The first line is enough to create the model object. The second line gets us our summary results. Does scoring lower, doing poorly, on test 1 predict improvement, performing better than one did on test 1 on test 2? Yes! But despite this significant p-value, we know from the previous plot we've seen that it is a weak relation. Let's take the model and test some points on the Logit line. For context, here's our graph of the values with instructions for how to get it. Now that R has given us the y-intercept and slope, we can also superimpose or draw the regression line. All values of y predicted will fall on this line. They must. Recalling our prior regression training, to predict a y value from an x or set of x's, we multiply that x by its slope or partial slope and add the intercept. In this case, the student scored a 76. Multiplying 76 by negative 0.06257 and adding the y-intercept of 4.79393, the result is a Logit value of 0.03861. Since pre-calculus or functions and relations was a long time ago for most of us, to make any sense of this, we need to recall the Logit to probability conversion from earlier. But before we convert, let's get another x value for illustration and comparison. What if the student had scored 40 on test 1? This would yield a Logit or y value of 2.29113, which is way off the graph, but rest assured it is on the line. It has to be. This is the straight regression line of predicted y values. On the y-axis here is the ln odds of improvement being predicted by test 1 score. We don't want the ln of anything. We want something interpretable. To get the probability of improvement, raise Euler's constant to the Logit, and then divide by 1 plus Euler's constant raised to that Logit. Plugging it in, this gives us 0.51. She has a 51% chance by our model of having a test 2 score that's higher than her test 1 score. This is a prediction specific to her score. This is admittedly not very impressive. We're saying that she has about a 50-50 chance of improving. That's why I had us take another example test score to compare. Let's get the probability of improvement. If her test 1 had been more objectively poor, a score of 40%. Her Logit score, the one that was way off the graph, of 2.29, converts to a proportion of 0.908, or a 91% chance of improving her test 1 score with a higher test 2 score. Note that this is where regression shines. Of course, it's going to be harder to improve a higher score and easier or more likely to improve a low score. In other words, of course, scores will tend to regress to the middle in proportion to their extremity. You don't bet on extreme values getting more extreme. But to what degree do we trust or use that fact, the fact of regression to the mean? Regression modeling lets us know. But hang on here, I thought logistic regression plots resulted in sigmoid curves and were nonlinear. Well, that magic happens when we convert the output, the logits, from the natural ln scale. Let's just plot the probabilities. Here, I create an object that is the probability values. In other words, the logits transformed out of the natural log scale by raising Euler's number to their value, and then converted from odds to probabilities. This is the same formula as we saw earlier. right here. The plot is the same, but our y variable is this newly computed object, the probabilities we obtained from the logits. Here's our curve, roughly sigmoid. Let's check our work. Let's make sure the two values we just computed do in fact fall on this line. First, there was the student's score of 76. Is the 0.51 proportion we calculated the correct value that we would find on the line? Looks like it. How about the 40% score? We couldn't check that one on the previous Logit graph. How about on this one? Yes, a score of 40% corresponds to a probability of 0.91 or a 91% chance of improving one's grade on the second test. We can eyeball from the graph that it is only the students who score above 80% on test 1 that really need to be concerned with regression to the mean, i.e. with not improving on test 2. We can recall here from the previous lecture that the size or magnitude of the slope captured in the standardized beta coefficient should tell us the degree of relation between the predictor and outcome variable. The logit is the ln of an odds ratio, so we could convert the computed parameter values from natural log scale. Raising Euler's number, e, to the slope coefficient, negative 0.06257, yields an odds ratio of 0.9393. So each unit increase in test 1 score, each percentage higher, is 0.94 of a unit decrease in odds of improvement on test 2. We can check our work in R. Here's a command to do that. I include the confidence intervals as a measure of the quality of the model. We would expect 95% of similar samples to result in models whose slope coefficients fall between 0.91 and 0.96. How good is the relation predicting probability of improvement from test 1 score? Not bad. There are other ways to get this sigmoid and prettier versions of it. Here's the code in ggplot. Just make sure you load the package first. Here we have the actual line, not just the predicted values that fall along it, so we can see the interpolated values as well. So the test 1 score is moderately helpful, but what if we had a more predictive piece of the student's work? Let's take a look at what a stronger relation would look like in a logistic regression model. Lab 3 score turns out to be the better predictor here. Our outcome, or dependent variable, is still the same. It is improvement from test 1 to test 2. We're switching to an independent variable or predictor that has better separation. That is, scoring higher on lab 3 is quite predictive of improving from test 1 to test 2. Our slope value for this model, 0.1141, is nearly double that of the previous model. And if we plot the relation using this code, getting this graph, we see from the plotted dots alone that there are plenty of low values on lab 3 that correspond to not improving, and very few low values on lab 3 that correspond with improving, and plenty of high values on lab 3 that correspond to improving, and very few high values that correspond with not improving. There's more separation on this plot, predicting improvement from lab 3 score, than on our previous plot, predicting improvement from test 1 score. If you prefer the non-ggplot graph, this is how to get it. In this case, improvers averaged much higher lab 3 scores. Those with higher test 2 scores than test 1 scores, improvers, averaged 47.9% on lab 3, while those whose test 2 score was the same or lower than their test 1 score, non-improvers, averaged 79% on lab 3. For each unit increase in lab 3 score, multiply our e to the y by 1.12. So each unit increase in lab 3 score, each percentage higher, is 1.12 of a unit increase in odds of improvement on test 2. Note that this neat conversion and its interpretation is only simple for this simple, i.e. one independent variable, log regression model. When we get partial slopes, things require a bit more effort to interpret. Speaking of multiple logistic regression, we now have two good predictors, which are probably independent of each other. So let's run the full model. Let's predict using both independent variables, both predictors. We have both pieces of information. Let's put them together. Here is the model. Here is our plot. Note the impressive score separation. Low predicted values correspond to lack of improvement and nearly never to improvement, and high predicted values correspond to improvement pretty much exclusively. Here are our 95% confidence intervals for the partial slope parameter estimates. They look pretty good as well. Here is the graph of predicted values and code to get it. So let's predict improvement in a way that shows the complexity of the model. This is the benefit of models in general. Most of us would not likely think there's too much of a difference between scoring 60% on test 1 and 71% on lab 3 versus scoring 60% on lab 3 and 71% on test 1. The values aren't that much different, so swapping the assessments to which each score belongs shouldn't make too much of a difference, right? But the model doesn't have our brain's tendency to use shortcuts and eliminate distinctions. As a result, we get very different probabilities of improvement. Let's say the student scored 60% on test 1 and 71% on lab 3. Here's our logit, 3.55922. Let's convert that from natural log scale, and then convert it from an odds ratio to a probability. Okay, so a relatively low score on test 1 and a higher score on lab 3 gives us a 97% probability that this student will improve on test 2. Let's just switch these seemingly quite similar values. What if the student got a 71% on test 1 and a 60% on lab 3? Here we have a negative logit and only a roughly 32% chance of improving. In other words, we're going to predict that this person's score is going to either be the same or lower on test 2 compared to test 1. The model is separating out predictions, making distinctions quite well. Finally, it should be the case that a 1-unit change in lab 3 grade, denoted as x2 here, decreases our odds ratio, denoted e to the y below, by 1.23 times. More precisely by 1.23174 times, because rounding errors here tend to get notable. In the multiple regression situation, this requires holding the other predictor variable constant, so we're comparing improvement in the dependent variable as a function of lab 3 score change at the same value of test 1, in this case set to 60%. While e to the y, the logit that has been back transformed from the log scale, since it's the odds ratio and not the probability or proportion, it's where we can see the meaning of the partial slope term. The difference here between scoring 71 and 72 on lab 3 shows up in the dependent variable as the score of 72%, resulting in an odds ratio that is 1.23 times the odds ratio from scoring 71%. That's the work that your partial slope is doing in the multiple log regression model, all the way down for every unit increase in lab 3 score. Note that the relation between lab 3 score and the logit, which is in the y column, is linear. The algorithm is working off of a straight line, the values along which back transform from, in this case, the natural log scale, to values described by a sigmoid. But your finding of an ideal line is being done linearly on the logit values. That's the trick or magic, which is why I opened with this straight line, along which all of the logit values fall. It's when you transform them back to odds ratios and probabilities that you get your nice sigmoid. That's all for today. Stay tuned.